We want to continue our discussion about vectors, vector spaces, and a specific vector space we'll talk about today, which is something we briefly talked about last time, is vectors in the plane. So how we're going to describe a vector and in a plane, we'll describe it as an action for right now. And then, remember, vector spaces are a set, right, with some binary operation on the set and some scalar multiplication on the set that satisfy some properties. So they can be whatever, the vectors can be whatever you want them to be. So in this case, we're going to describe vectors as actions. And that's perfectly fine. They don't have to be physical objects. So in this case, this is how we're going to define vectors. So we're going to think about vectors as the action of jumping a certain distance in a certain direction. So notice the definition of that it doesn't matter where you are when you jump. It doesn't matter where you are when you land, but it's just the act of doing that. So if I am right here and I'm jumping a certain distance, so that's going to be somewhere along the circle and in a certain direction, so the direction chooses where I point, and I jump a certain amount, then that whole action will be, that's going to be our description of a vector. So this whole thing will be, this action will be the vector. So it's not, the arrow is just kind of like a representation of what the action is. For right now, we don't have to consider it so literally, physically like an arrow, but imagine it as the action of doing this jump. And we'll see how this relates back to kind of what we've been thinking, vectors like as a kind of a 2-coordinate object, but we'll kind of relate that in a bit. So the question is, if I want to say this is a vector, I have to prove if it's a vector space. So I need some binary operation and I need some scalar multiplication. So first of all, does that make sense as an object in my set, as this action of jumping a amount in a direction? Any questions on that, just on that definition? Okay, so here is how we're going to describe our binary operation, right? We need a binary operation if we talk about vector spaces. So what does it mean to add jumps together? So remember, adding, don't focus too much on the word add, just focus on binary operation. So this is how we're going to add, and it's going to be kind of very simple. It's going to mean first jump V, then do jump W. So if I'm right here and I jump V, I go to V. So now I'm landed here, and now I'm jumping W. So now I jump W. So I jump V and I jump W. So the sum of two vectors in this world will be jumping V, then jumping W. Yeah, so I mean, how could we describe, so when we talk about maybe closed, oh yeah, so sure, okay, so let's kind of describe that. So what is the vector V plus W? Let's talk about its properties. So it has some distance and it has some direction. So how will we describe the distance? We'll describe it as displacement. Yeah, so it's how far did you go from where you started? How far did you end up from where you started? So it's not going to be the length of, it's not going to be this length, right? It's not length of V plus length of W, but it's going to be the displacement. So the distance from from the start. Does that make sense? So we're not adding up the distances, but we're seeing how far did we end up from where we started. And same thing as direction. It's direction from start. Right. So if you put those two together, right, the line from our beginning connecting from our end, right, that will be the displacement. The length of that line will be the displacement, and the direction we can describe by an arrow, where that's the direction we ended up. That vector, it will be called v plus w. So it's still an arrow, right? We're saying so we're just still describing it as a single vector, but we're describing it so in two ways, right? Both as kind of the result of kind of doing this double jump, and we're saying that we'll call it the same as doing a single jump, doing v plus w jump. So those will be called the same vectors, the act of jumping v, then w, and then someone else just jumps v plus w. So those will be called the same. Does that make sense as adding vectors? Okay, great. All right, so we'll have to prove that that satisfies all the axioms, right? So as we're continuing, try to think about how would you go proving that. Okay, now let's do scalar multiplication. What does it mean to multiply a jump by a number? All right, so this is a bit more straightforward. If I have a jump v, what is 2v? It's just going to mean jump twice as far. So if this is v and this is v, then if I'm jumping twice as far, we're going to call that 2v. That's all. That's all we're doing with scalar multiplication, just jumping twice as far. I'm not changing the direction yet. So multiplying by a number just means, well, 2, for example, jump twice as far. Can someone guess what half would be? What would half be? So if this is v, what do you think half v would be? Jump half as far. Jump half as far. Good. So, draw where the midpoint in that arrow, and then draw a little arrow, and this is half v. Okay. Any questions about that? All right, so now let's talk about negative v. So here's v. Can you guess what negative v? Good, opposite direction. So it's opposite direction, but same amount. Jump opposite direction, but same amount. Okay. And what do you imagine 0v would be? So putting all these things together, what do you imagine 0v would be? Yeah, so don't jump. So don't jump at all, right? Because if the number in front is scaling the vector by a certain amount, right? If it's 2v, you jump twice as far. Half v, jump half as far. Negative v, jump the opposite direction. 0v is you're removing all distance in the jump. So it's just, well, maybe you can think of instead of don't jump at all, because we want all these things to be jumps, say jump in place. So you're just jumping up and down and not moving. Okay, so the 0 is this point here, right? That's 0, the vector 0. Yeah, so let's describe that. So 0 is jumping in place. Okay. All right, so any questions just on our setup of what jumping is, how you add jumps, and how you scalar multiply jumps? So now we need to go through all those axioms. There's like 8 or 10 of them, right? To see if this forms a vector space. Okay, so what's our first axiom for vector spaces? So let's start with the binary operations. So binary operation axioms. What was our first one, or our 0th one? Closed, yeah. So what do you think we would need to check for closed? How do we describe that in terms of our jumps? So what do you mean by quadrant? Or closed is just, you want to check what do you want to check about the sum of 2 vectors? What does closed mean? Yeah, is the sum a vector? Right. So in other words, is there a pair of vectors? Is there a pair of jumps where their sum is not a jump? Is that true? Can you find 2 vectors whose sum is not a jump? And remember, jump in place is fine. Yes. V plus W is always a jump. And why is that physically? You can always make a triangle, right? Can always make a triangle with 2 lines, essentially. Or if they're in the same line, then you just, if parallel, the sum is just the continuation. Yeah, so what if W is equal to negative V? So if this is V and this is negative V, what is the sum? Well, the sum is the jump in place vector, right? Jump in place. Right. So it's still okay as a jump, but you're just not going anywhere. Yeah, so these 3 scenarios we have, if they're pointing in opposite directions, you can always make a triangle, right? If they're pointing in the same direction, you just continue the line. Or if they're pointing in opposite directions, right, then they would cancel down to 0. So maybe let's talk about negative vectors. So if let's say V and W are same direction. Or let's say W is opposite direction to V. So let's say this is V and this is W. Let's just make it shorter. So what is V plus W? So based on our jump definition, first you do V, and then you do W. So what's left over is the net jump is V plus W. So I'm going back a bit. Does that make sense if you have opposite directions? It's kind of analogous to if they're parallel, right? But you just kind of jump backwards. So yeah, what would V minus W mean? Minus just means well, we'll talk about that. What does this mean? It's just plus negative, right? We'll describe maybe why negative means what we think it means, maybe additive inverse, right? So that makes sense? So we'll describe how subtraction works physically. But first, let's go through all those axioms. Okay, so cool. So we proved it's closed. That's great. So every pair of jumps, you can always add and get a new jump. Great. Yeah, so this is the sum. Okay, so let's give another act. So what's one of the axioms for addition? So we did closed. What would another axiom be? This is for the binary op. Sure, we can do associative. So I think this was our second op, but we can do this one first, associative. Okay, so what does that mean? If you have a sum of three things, can someone say in words what that means? What does that mean in words, associative? Good, yeah, it can be added in any order. So if you're a fan of adding the first two and then adding the last, that's fine. And if you're a fan of adding the last two and then the first, that's fine. So let's prove that. So now this is not a really rigorous proof. It's kind of pictures. So just keep that in mind. Let's do this way. So let's do V, W, and Z. Okay, so first let's do V plus W. All right, so we go V, and then we go W, and then we connect them. This is the result of adding. And let's draw Z a little different to make it look. Let's do it like that. And then we're doing Z down. We're plussing Z. Okay, so this is V plus W. This is V, W, Z. Yeah, we want to show the displacement is the same. Yeah, that's the goal. So this is, yeah, so this is V plus W plus Z. Does that make sense? Okay, so let's do the same thing. So the three VWZ will be the same, right? V, W, Z. But in this case, we want to look at W plus Z first. So let's do that first. That's W plus Z. This is Z. And notice that we're still connecting the last 2 points together, right? We're still connecting the last 2 points. In both cases, right? The V plus W plus Z is always starting from the starting point and ending at the ending point. So I think just describing these things as jumps, it's kind of obvious why it's associative, right? You always start at the same place and you always end at the same place, regardless of how you order it or how you group it. Okay, does that make sense? We're always starting and ending at the same place. Okay, great. All right, so what's the other thing we need in a vector space? What's the other commutative? Yeah. So we can be a little bit more geometric with this one. So what does commutative mean? 5v plus w, what should that be the same as? W plus v. Okay, so let's let that be v, and let's let that be w. So first I go v, and then I go w. So I connect the two, and this is v plus w. Okay, so now let's be a little bit geometric. What happens if I do w first? So if I start here and I do w first, what do I know about these? These are both w's. Geometrically, what do I know about those two lines and why? They're parallel, and why are they parallel? What about our, yeah, they're the same direction. They have to be, right? They're the same vector. Same direction. Same vector. Okay, so now if we jump v from w, what do we know about the two v's? Parallel as well. And what else do we know about the v's and the w's? And same length, yeah. Right, and same length, because they're the same vector. Okay, so what do we get? What type of object do we get when we look at all the v's and w's in the same picture? It's not necessarily a square, but what's more general than a square? Even more general than a rhombus. Rhombus would imply all the sides are equal. Even more general than a rectangle, right? Rectangle would mean all of those angles are right angles. Parallelogram, right? This forms a parallelogram. Right, and why is that? Because we have equal sides and equal and parallel sides. Now, what's nice about the parallelogram, and which proves commutativity, is that what is w plus v? Well, it's the same what do you call it? Same diagonal, right? So so that proves it. So a parallelogram, the diagonal that you form will always be the same, regardless of v plus w or w plus v. All right, any questions on that? Okay, so what is another binary axiom we have? Identity, yeah. What do you think our identity vector is? So if I have v, what vector do I add? Yeah, what we call the zero vector. So this is the jump in place. Okay, so let's do that. So let's say I start here and I jump V. Okay, now I land at this point. And now let's add 0. So it's kind of like I just jump in place and come back down. So what is the sum of the two vectors? Well, I started here and I ended here, so I draw an arrow and I get V back. Good, all right. And the same thing, if I wanted to kind of jump in place first and then do V, then I also get V back. 0 plus V is equal to V. So that's our identity. All right, what's next? What's after identity? So we're still on the binary operation, inverse. Yeah, I think identity and inverse come in a pair. Okay, so if I have V here, what vector would I need to do? What jump would I need to do? Good. What jump do I need to do to get back to where I started? Well, if you just think about it physically, if I jump this way by V, how do I get back to where I started? Well, I have to jump in the opposite direction and at the same amount. So I have to jump negative V back. Negative V. And so what is the sum of those two? 0. So it's the jump that you just jump in place. So if someone jumped V and then jumped V back, it's the same as someone else just jumping right in place. They ended up at the same place. All right, great. So that is all the binary operations, right? So that satisfies all those the binary axioms. Okay, so now let's do other ones, the scalar axioms. So what's our 0th scalar axiom? Closed, yeah. So to do closed, let's kind of be more, let's be a little bit more rigorous. Because you might want to say how, so we know how like multiplying by integers work, right? We know how to multiply by fractions, what that does. But what does multiplying by pi do, for example? So let's explain, really what that does. So how do we describe alpha V? It's scaling the distance by alpha. So it's multiplying the distance by alpha. So first of all, let's describe what distance means, right? What I want to do is say, well, alpha V will always give me a vector, will always give me a distance and a direction. So let's just make sure that the distance of a vector can be described explicitly, and how multiplying with alpha would affect that. Okay, so let's look at a plane, or xy plane, and let's look at a vector. Let's do starting from 0, and let's do a jump. Okay, can someone tell me how to describe the length of that arrow? So now that we are on a coordinate system, we can probably actually explicitly calculate that. So yeah, how do you find length of a line? XY. Okay, so let's call this point XY. Is that what you mean? We can call this point XY. So we're saying that if we start at 0, 0 and we end at xy, that's going to be our vector. So how do you describe the length of that? So just imagine this as distance traveled. Good. So this is just the Pythagorean theorem, right? What's this length here? And what's this length here? Based on the coordinate is x and y, yeah, x and y. So the length is our nice x squared plus y squared. Good. All right, now tell me, what does alpha do? Alpha multiplies distance. Or we can just say length right now. So what is the length of alpha v? Where v ends at xy. What do you think the length of alpha v would be? I mean, not a trick question. Exactly, alpha multiplies the length. So length of alpha v is just alpha times x squared plus y squared, right? That's it, good. All right, so now, how can we, do you know how to bring alpha inside the square root? First, let's suppose, yeah, how do you bring alpha inside the square root? Good, yeah, you treat it as square root of alpha squared. So can you always bring alpha inside? Yeah, so you can say, maybe I should have put an absolute value here, right? Because if alpha is negative, we're not doing negative length. Right, so this is square root of alpha squared. Oops. Good, that's exactly what absolute value is. Now let's bring alpha inside. So alpha squared times x squared plus y squared. Okay, so what can I do now? I want to see where x and y go. What do I do now? So I can distribute, right? Get alpha x squared plus alpha y squared. Right. So in describing alpha, how we described it in the beginning is just we're multiplying the distance, right? It turns out that multiplying the distance by a certain amount is equivalent to saying you're multiplying, if you start from 0, 0, you're multiplying right, the end coordinate by alpha. So you tell me, why did I put that in a straight line? Why is alpha x, alpha y in the same line as xy? Why is it collinear? Like, why didn't I put, why isn't alpha x, alpha y here? Can someone say why that's true? Yeah, right. It's just, this is just scaling. So in other words, if this is x and this is y, this would be alpha x, right? And this is alpha y. So and you make similar triangles, right? So yeah, so that's scalar multiplication of a jump. So why is doing this helpful for discussing closed is because this allows us to talk about something like pi times a vector, right? Where something that's not as clear of how it scales, right? And here, what we're describing in this way, we can say what it does to the actual numbers. So if I describe the jump starting from 0 and ending at xy, what does alpha times the vector do? Well, it's the vector that's equivalent to starting at 0 and then ending at alpha x, alpha y. So since we describe it purely in geometric terms, then we can safely say that it's closed. All right, so any questions on that? So we did a couple of things here, right? We said we've discovered length of a vector if it's described this way, and how multiplying a number to a vector affects the coordinates if in coordinate form. Okay, so let's do what's one of the axioms for scalar multiplication. So after closed, what was some of our other ones? Distributive, yeah. So which one do you want to do first? Let's do over vectors. So we want to prove that alpha times v plus w is equal to alpha v plus alpha w. Okay, so let's let this be v, let this be w. Let's let this be alpha v. Let's just, why don't we make it, let's just make it twice for right now. Let's make it 2v. I'm not being rigorous right now. And then what would 2w be? All right. Yeah, so first of all, so yeah, we know what the addition is. So this is v and this is w. What is the sum? It's v plus w. And now let's do the case for 2. Now let's multiply the length by 2. So let's take another v plus w essentially. And so this, the full arrow will be 2v plus w. 2v plus w. So we want to show that it's the same as scaling each w and v, and we want to make sure we land at the same place. Okay, so now let's multiply v and w by 2. So v gets multiplied by 2. I go up here, and if I multiply w by 2 and add it to this 2v, we just want to verify that it truly goes there. So this would be like 2w. All right, so this is 2v, and this is 2w. All right, so let's just make sure that's true. Is it true that I will land at the same place? Well, this is just this is similar triangles, right? I get sorry, what? Yeah, so this is 2 times v plus w, right? And this one is, oh, sorry, I meant 2v. Yes, thank you. Yeah, so this length is 2v. This length is 2w. Oops. W, V. Oh, sorry. This is V plus W. This is V. This is 2V plus W, and this is 2V. So this makes similar triangles, right? I have my first triangle in here, and then I have my bigger triangle out here. So scaling by any number, doesn't have to be 2, will always construct similar triangles. So it's a nice picture of distributivity of a scalar. Okay, so do you see the difference? So first one is V plus W times 2, and the second one is 2V plus 2W. So I'm always landing at the same place, if you think of it as like a path. Okay, so let's do another one. What's the other distributivity? Over scalar, yeah. It's like alpha plus beta times V, and you want it equal to alpha V plus beta V. All right, so let's just this be V, and let's make alpha equal to 2 again, and let's make beta equal to 3. All right. I'm not being rigorous with this. I'm just trying to geometrically kind of show what's going on. So let's do alpha V plus beta V first. All right. So if this is V, let's do alpha V. So alpha V is just 2V. This is 2V. And now I want to add 3V to this. So from here, I want to tack on 3 more V's. So 1, 2, 3. This whole thing is, this is 2V, and then this is plus 3V. And again, this is right. This is of course same as alpha plus beta V. If this is V and I want to do alpha plus beta V, it's 5V. So 1, 3, 4, 5. This is 5V. All right, so you see the difference. So the first hand I'm doing 2V plus 3V. On the other hand, I'm doing 2 plus 3 times V, which is 5V. So this is 2 plus 3 times V. So that's what distributive means. I can do either I can do the addition first in the scalars and then multiply by V, or I can distribute the V in and then do each scalar multiplication. All right, this one's not too bad, but any questions on that? Okay, so let's do, next one is, yes, these are the same length because, right, this is 2V and this is 3V. Yeah, so at every point there are 5 V's total. Okay, so the next one is, what's the next one? This one's kind of the interesting one. So I have distributive vectors, distributive scalars. doesn't have to be the next one, but what is a scalar axiom that you know? Sure, we can do identities. This one is our fourth one. Identity preserving. Okay, so 1, the number times v, what should that equal? V. Is that true? What do we know about 1 times v? What does that do to the vector? What does this do? So in our initial definition of scalar multiplication, what does 1 times a vector do? Do v 1 time or multiply distance by 1, right? Multiply distance by 1. But that doesn't do anything, right? So of course it's the same. So v, and then if you multiply the distance by 1, well, you don't go anywhere. You stay just as v. Okay, so what was the other axiom? Compatible, right? Compatible with field, yeah. So that means if I can multiply in the field first and then scalar multiply with a vector, or I can do the scalar multiplication twice. So I can first do beta on the vector and then alpha on that. This one I won't go too in depth with, but because it's kind of hard to geometrically describe a product. I mean, it's just a bit more involved, but yeah, so actually, why don't we do it by length? So let's say the vector is, as we did before, if this is 0, 0, and this is xy, right? What is beta v going to? So if the length of v would be x squared plus y squared, right? Square root. What is the length of beta v? So remember, all we described scalar multiplication is changing the length by amount. Exactly, just beta times x squared plus y squared. Square root of x squared plus y squared. And now, what is the length of alpha times beta v? We tack on an alpha, right? Alpha times beta times x squared plus y squared. Okay, so that's the first, the right part. Now the left part is a little easier, right? So now you just do the length of alpha beta v. So you just multiply that by alpha beta. Well, of course, there's absolute values here, by the way. Just want to make sure the length is, if it's negative, that's it would get reversed. So so all we need to say is, why are these equal? And you tell me why they're equal. I don't do betas today. Why are these equal? Is that true? Can I split up a product in absolute value? Yeah, they're absolute values, right? It doesn't matter if either alpha, beta are negative, right? Because the absolute values will always be the same. Yes, it's the sum where there's a problem. All right, cool. So that's it. That means it's a vector space. So it's a vector space. All right, good. So we had to go through all those axioms to prove it was a vector space. So now that we know it's a vector space, now we can describe how to talk about adding vectors. So this will be called so vectors on a plane. So the claim is that they're the same as vectors in R2. So, and we kind of already talked about this. So this jump is equivalent to looking at the jump from 0, 0 ending at xy. So the jump from 0, 0 ending at xy will call, the vector will be called xy. That's what we're going to call the vector. So the jump in that direction at that amount, if we jump instead at 0, 0, we're going to call that jump xy, the vector xy. So it's the jump x to the right and y up. That's what we're going to call the vector xy. Questions about that? So let's just do an example. What is this vector? 1, 0. Describe that vector as a jump. Yeah, 1 to the right. So the first position is my right and left if it's negative, right? So I'm doing 1 jump to the right and nothing up. Okay, what is 1, 2? So what would that one be? Yeah, I'm going 1 to the right. Yeah, I'm making my 1 smaller. Going 1 to the right and 2 up. So that's 1, 2, the vector 1, 2. Notice I'm not starting at 0, right? This can be anywhere. This could be over here, right? Because my vector action is just relative to just the jump itself. Doesn't matter if that 0, 0. Let's do another one. Let's do -1, -3. What would that jump be? Yeah, 1 to the left and 3 down. So that vector is -1, -3. Okay, great. So now let's see how this works with addition. Now that we've kind of like clearly established, what they look like, as numbers, let's see how the addition might be compatible. Okay, so let's have, we have the vector xy, and we want to add the vector ab. So let's say this is the vector xy. So what does that mean? Can I describe this triangle? How can I describe this triangle? What is this? And what is this? Yeah, it's x to the right and y up. right? So, and let's say we have this vector, AB. Okay. What are these? Well, A right and B down. Yes, this is A. Well, yeah, so B would be up, right? But I guess since B is down, B is a negative number, right? B is a negative number. All right, so let's.
How do we decide which side we label as what variable?
Yeah, so the first entry is your horizontal. That's how we defined it. And your second entry is your vertical. Right, so in this case, our B was our vertical and A was the horizontal.
And that's always the case, no matter how you draw the vectors?
Yeah, yeah.
Thank you.
Yeah, so I kind of drew it a different way, right? I could have drawn it this way, right? I just happened to draw it. Yeah, so let's see what adding vectors would do. So let's take the vector xy. Oh no, it's just this is just the length. The length of the dotted line is x. That's all. And the length of this dotted line is y. Right, because they're vertical and horizontal. Yeah. Right. So the idea is that this length is y. I'm going to put on this side. And this length is x. I'm not referencing to the x-axis for a reason. Just these are just jumps out on the plane. And so now we want to add the vector AB. All right, so let's describe what the vector is. So let's do different dotted lines. So let's do it actually over here. So again, what is this length? A. And what is this length? B, yeah. Okay, so what is the sum? Well, how we define it in the beginning was we would connect the beginning and the end point, right? Good, yeah. So what is the x? What is the horizontal length? Is x plus a, right? It's x here, and then it's a here. Good. And then what's the b or the vertical? Yeah, y plus b. So b is like negative here, so it takes away, right? So this here is y plus b. So remember, b is negative. So what is the vector sum? So x y plus ab is x plus a, y plus b. Cool. So so we're matching a y is b negative because it's down, right? So we described, so the vector xy is, it's a jump x to the right and y up. So if I'm going down, that means the y was negative. If I was going to the left, x would have been negative. So I'm going down, it's negative. So that's why it takes away. So, right, this is kind of, this is negative. So it takes away this stuff, right? that gets eliminated by B. Yeah, this is all, you can all think of this as on a graph, right? This is X, this is Y, this would be X plus A, this length would be A, what's this? Well, this length would be at least absolute value of B, but it's negative. Yeah, so again, we're just relating what we know about how we described our vector space in terms of jumps, and we're seeing how it's related to something we already know as a vector space as vectors in R2. So we're saying these are really the same thing. So which is nice. So we can actually, we don't have to use geometry anymore, right? When we talk about vectors in R2, we can just, or on a plane, right? We can just say it's that's the sum. We don't really have to go through the jumps. But I like, the jumps are nice. What's the nice thing about jumps? It's nicer than this description of addition because, you know, jumps, you can look at it, right? You can physically look at what the vector is. Where this definition here is it's a little bit too abstract, right? But it's nice that they can match. So yeah, so let's kind of do some examples of adding and subtracting. Yeah, well, actually, let's talk about subtracting. Okay, so let's think about subtracting vectors. First, we'll do it completely graphically. So V minus W. So remind me, what is the better way of saying V minus W? Remember, subtraction is not fun. Yeah, you just say V plus negative W. Okay. All right, so let's let this be V. And let's let that be W. What does negative W look like? What's negative W look like? Yeah, it's the same thing, but the other direction. Yeah. Okay, so let's take V. And to V, we're going to add negative W. So here is negative W. And the sum, right, is connecting the beginning point to the end points. This is V minus, this is V plus negative W. Okay, but now let's see, let's look at W from the same starting point. So how do I draw W? Well, it's going to be this kind of direction, but pointed this way. All right, so can someone tell me why these are parallel lines? This is W, right? Why are those parallel lines?
Because they're going in the opposite directions.
Right. So they're just pointing in the opposite direction, but they're still like they would be different by like 180, right? So these are parallel and in the same same direction. So let's take this point here. This is V plus negative W, and let's see why this is actually the same as this line here. This is also V plus negative W. For the sake of time, I won't rigorously go through that, but the idea is that if you subtract vectors, just as we went through here through the jumps, the equal and parallel line from here is v minus w. So this is v minus w. So v minus w starts at the end of w and ends at the end of v. So it's forming a triangle from the -1 to the +1. So this is v minus w.
Since we're illustrating v minus w on there, would v plus w be just that line, but in the opposite direction?
Oh, so, well, I mean, just think about it. What you're describing as negative v minus w, right? That would be w minus v. You see that?
Yeah, so the opposite wouldn't really be w plus v.
Right. Well, what is w plus v? This is what we described before. This was the parallelogram. So if I do w and then I do, or sorry, if I do v and then I do w, the sum is connecting the two lines, or the two points. And this constructs a parallelogram. So the sum of two vectors is the parallelogram formed, and the subtraction of two vectors is completing the triangle formed. So this is v, and this is w. So this is v, and this is w. This way would be w minus v. That's what you're saying. So this would be w minus v. So see the three scenarios?
Yeah, that makes sense.
Yeah. So again, these still come from parallelograms, right? The subtractions, but since we're talking about negative, we have to, it's a different way of describing the parallelogram. Yeah, so I'm just taking a piece of the parallelogram and that describes the subtraction. Yes, this is equals to. All right, so, and again, I think the better way of talking about subtraction, if you forget kind of where the arrows should go, just remember it's just adding the negative, and I think it will be easier. So I know, this is kind of a conventional way to talk about subtraction, right? By completing the triangle. But I personally think it would be easy, because I always forget, where the arrow goes, right? But I think if you treat it as addition, then it's kind of obvious where the arrow should go. Okay, yeah, any questions on that? So for drawing, this is how we're adding and subtracting. But again, for subtracting, I like treating it as adding the negative. Yes, the arrow points towards the +1. Yeah. And again, if you forget, just treat it as a sum. Yeah, it leaves the negative and points towards the positive. Okay, so yeah, I guess let's do some examples. Let's do 1, 2 plus -1, -1. All right, so we know what this is, since we know it's right similar to just R2. What should this be equal to? Zero, one, yeah. Should be equal to 0, 1. That's all right. 0, 1. So now let's draw the picture and see if it makes sense. Right, yeah, or 0, right, 1 up. Yeah, so here is 1, 2. So let's do that. So it's 1 to the right and 2 up. And let's look at -1, -1. So the 1 is too big. So here is 1, -1. Okay, I think I need to make sure everything is perfect. Let's say that it's about right. Okay, so let's try this again. All right, so here is 1, 2. Here is -1, -1. And I want to look at their sum. Okay, so let's take, if I want to look at -1, -1 here, starting from here, where does this point to? So if this is the point 1, 2, now let's do the -1, -1 vector. Where does this point to? So remember the vector as an action, a jump. If I start at 1, 2 and I do the -1, -1 jump, where do I end up?
1, 1.
1, 1 would be here, right? Okay, yeah, 0.
0, 1 then.
Yeah, so it would be, yeah, I'd be here at 0, 1. Right. Okay, so now let's do so if we connect the so doing 1, 2 here, I get there, and then what is the sum? So the sum of the two vectors is drawing the diagonal and the parallelogram. So both arrows point at 1, 1. So the sum is 0, 1 by drawing it. So we've assured ourselves that 0, 1 truly is the sum. Everyone see that? Oops, remember with all that. Great. Yeah, so this here, this is the -1, -1 vector, but where my starting point is 1, 2. Okay, cool. So great, that's 3.1. So we've related it back to the plane. Next time we'll talk about subspaces. So that'll be Wednesday. So yeah, I'll see you then. So I'll stop recording.